Okay, Bismillahirrahmanirrahim. So now we are going to start this CO5, which is about mathematical induction and the recursion. Just a minute, I have to look for the pointer. Yeah. So here in this CO5, we have to go into the details of mathematical induction and then some recursive approaches. This CO can be expanded and can be reduced. So I have tried something which is not something expanded, not something reduced. It is in between. So you will see that thing. So what is mathematical induction? Have you ever heard about mathematical induction before? This is a principle. You can say Qanun. Qanun is Arabic word, okay? So this is mathematical induction. And normally we use this mathematical induction to prove something. We normally use this mathematical induction to prove something, the complexity of algorithm, the correctness of algorithm or programs, or to prove some kind of a theorem about graphs and trees, or to prove some identities. Identity means just went into the chapter 1 and 2, and then you have something on the left hand side and the right hand side, and both are equaling with the one value, with the true value or false value or whatever, the same, left hand side and the right side. So those are identities and inequalities. If left hand side is not equal to the right hand side, so we can use this mathematical induction to prove things like that. Even you can use mathematical induction beyond this. And what is mathematical induction? This is just a picture to give you an idea that if you are standing on the ground and if you are looking at this ladder, then you can imagine that I can reach at step 1, because you only have to make a little bit step forward, and then you can reach at step 1. Similarly, when you are at step 2, then you can say that I can reach at the step 2, and so on, and so on. And if you are at step k, then k plus 1 is the next step. So then you can say that I can reach at the k plus 1 step. Only one step forward, not too much. Even I can think, even on the ground, you can think that I can reach at the top or whatever. But this is an infinite series, okay? This is a concept of infinite thing. You can imagine whatever you want. But what is mathematical induction? This is the picture for elaborating the concept of mathematical induction. That if you are on the ground, then you can take it as a privilege that you can reach at the step 1. And if you are at step 1, then you can, it is your right, you can say, that you can say that I can reach at step 2. And similarly, when you would be at step k, you can say now I can reach at the step 2. So basically in mathematical induction, there are 2 steps. There are 2 steps. Anyhow, leave it. We will see it, these 2 steps in the next slide. So, but here we are trying to elaborate those 2 steps in general words with respect to this example. So if you are on the ground, you can say that I can reach at the first rung of the ladder. This is called rung. This is called rung, step. I can reach at the first rung of the ladder. And if you will reach at some particular rung at any step, uh, of the ladder, then you can reach the next rung or next step. If you, for example, if you are at this step, then you can say I can reach at this step. If you are at any particular step, particular means makhsus, particular step, then you can say that I can reach the next step. And for example, if I say that if we have used 100, if we use this step number 2 100 times from the ground, then we are at, maybe we are at step number 100. We are at step number 100. And when you are at step number 100, then you can say that I can reach at 101. I am repeating different things, same thing again and again. Why? Because only then this concept will be in your mind. So if I am at step 100, then you can say that I can reach at step 101, which is mentioned here. But if this ladder is infinite, then there is a question that can you reach every step or every rung of this ladder? You are standing on the ground and the ladder is infinite. And the question is, can you reach every rung of this infinite ladder? And the answer of this question, you are on the ground, okay? And the answer of this question is yes, you can reach at every step or every rung of the ladder. And the similar things, and for this, you have to use mathematical induction. And to prove this theory that can you reach every rung of this infinite ladder, the answer is yes, but to prove it, you have to use the mathematical induction. Similarly, now in upcoming slides, the problem like that will come, and then you are on the ground, you can say, maybe on that ground, maybe. So you have to use mathematical induction, and then you have to prove that problem in that infinite domain, whatever the problem will be given to you. Now, moving forward, now we will talk something specific to mathematical induction. That was the general discussion. Now we will talk about specific to mathematical induction. If you want to prove something, like the question here, if you want to prove something, then the first thing that you have to do from the given problem, that you have to identify the propositional function. You have to identify the propositional function. What is the propositional function in that given problem? If the problem will be given to you, you have to identify the propositional function, the proposition actually. And you can represent that propositional function with P of n. And what is n? N is positive integers, all positive integers. So infinite, all positive integers. So that is something fixed for mathematical induction. So you have to identify the propositional function, and that you can represent that propositional function with P of n. And then you have to show that this propositional function is true for all the positive integers n, for all the positive integers. This is what you have to show. Again, in a mathematical induction, if some problem will be given to you, you have to identify the propositional function P of n. P means propositional function. And then you have to show that this P of n is true for all positive integers. The domain is what? What is the area for which you have to solve the problem? That area is called domain. So that is the all positive integers n. You have to show that this propositional function P of n is true for all positive integers n. That is your main objective when the problem will be given to you. And then this mathematical induction has two parts. When you are going to prove it, you have to evaluate that problem by using these two steps. The first step is called basis step. I don't know, this is Arabic word or not, bunyad. I don't know. Bunyad is Arabic word? Bunyad. Yeah, foundation. What is the Arabic word? Asas. Yeah. Another name is asas. So anyhow, so basis, so that is something you can say asas or whatever, foundation step. The basis step. And the other step is inductive step. You have to evaluate these two steps, and only then you can prove that that propositional function is true for all positive integers. So mathematical induction has these two parts, basis step and inductive step. And what is basis step? In the basis step, you have to show that P of 1 is true. That is the first step. For example, in the ladder, this step 1 is the basis step. Okay. So you have to show that if some problem will be given to you, some sequence, some series, some formula, whatever given to you, you have to look over what is the basic step. And then that basic step, you are calling it P of 1. And then you have to put this one value in place of that n, and then you will have to evaluate, and then you have to show that P of 1 is true. We will see how you can do that, but just keep this in your mind. This is the basic step. This can be P of 1, this can be P of 0, this can be P of 5, this can be P of 4. It depends on the problem. Foundation step, basis step. And then inductive step. In the inductive step, you have to show that P of k, you have to assume something first, and that assumption is here. You have to assume that P of k is true for all positive integers k. You have to assume it first, and by taking that assumption, you have to apply that assumption for the next step, pk plus 1. P of k plus 1. You have to apply that assumption on the next step. And if pk is true, you have to assume that pk is true, and then you have to apply that assumption on pk plus 1. And if that is also true, only then you can say that whatever the problem is, that is true for all positive integers. We will see. So this whole theory, which is written here in step 2, you can just write it in mathematical notation, so that the idea, the concept will always remain in your mind. You don't have to remember these words if this mathematical notation is in your mind. What this mathematical notation is saying, that P of 1 is true, and for every k, for every positive integer k, if P of k is true, implies pk plus 1 is also true. This is what the predicates. P of k is true. If P of k is true, why I'm using if? Because I know this. This is the predicate I can say. If then. So if pk is true, then pk plus 1 is also true for every positive integer k. And if this is happening, for example, if this condition 1 and condition 2 with respect to this conjunction is true, then finally you can say that P of n, the propositional function, is true for all positive integers n, for every positive integer. This is the illustration of this mathematical notation, if you have the understanding. Mostly people are looking at their mobile phones. I don't know. So because I am just highlighting things here, so it is better to look at here for better understanding rather than on the mobile phones. Because on the mobile phones, you don't have these drawings, which is giving you the idea. So that's why if I will ask now that what this equation is saying, then maybe the people who are looking at their mobile phones, they will not give me the answer of this question. So what is this? So what this mathematical equation is saying, this mathematical equation is saying the whole story that we already have narrated. And what is that story? That first you have to check that P of 1 is true. And then conjunction and. And then this is the second condition. This is the second condition. That for all positive, for every positive integer k, if pk is true, this due to this arrow, I am saying this if, this is if then condition. So if pk is true, then pk plus 1 is also true. And if both these conditions, condition 1 and condition 2 are true, now this is again arrow. So it means if these both are true, if I'm using again if this whole is true, then I can say that P of n is true for all positive integers n. This is the whole story that we have taken from these previous points, previous bullets. And this last point is saying that if you have any conjecture means a small theorem, or I am using the word theorem, otherwise in Arabic the best word is mafruda, okay? A small hypothesis, okay? Small, if you have some small hypothesis which you have evaluated and you have seen many times that it is true, but you don't have any proof. So for small conjectures, you can also use this mathematical induction to prove them. To prove a small conjecture, you can use also the mathematical induction. But for proving theorem, you cannot use the mathematical induction, because theorem is a bigger thing. That is not something you can prove a theorem by using this induction, no. But for small things, you can use this mathematical induction. This is again a picture. You will start from step 1. It will go like that in a sequence, okay? Now we have the example 1 to understand this mathematical induction. And the problem is, and the question is that show that if n is a positive integer, then 1 plus 2 plus and so on plus n is equal to n into n plus 1 divided by 2. So this is now given to you. The domain is positive integers. The domain is positive integers. Domain is positive integers. And then you have to show this one. This is the left hand side is equal to the right hand side, you can say. N is used in this equation. And what is n? N is positive integer. You have to show that. You have to prove that. And what this equation is saying, that if you will add all positive integers up to n, up to some limit, then you can simply take their sum, you can simply take their result by using that equation. You don't have to add them individually. You can use that equation, n into n plus 1, and then divide it by 2, you will have your answer of those 100 numbers or whatever, if they are in the sequence. If they are in the sequence. So now the first thing, so what I said in the previous, first you have to identify the propositional function, P of n. And after that, you have to evaluate 2 steps. The first one is basis and the second one is inductive. Inductive step has 2 sub-steps in it. The first one is assumption. You have to assume something, which is P of k. And the next is P of k plus 1, which you have to evaluate. And if they would be true, then you can finally say that P of n, your propositional function, is true for that domain. So now show that if n is a positive integer, then this 1 plus 2 plus and so on plus n is equal to n into n plus 1 divided by 2. So you have to show that this equation, whatever it is, this thing, whatever it is, you have to show that this is true for all positive integers. This is the question. This is the question, okay? You have to show what? You have to show that this left-hand side and right-hand side, whatever it is, this is true. This is true for all positive integers. And what is the first thing? You have to identify the proposition. And proposition is this thing. This is true for, so let P of n. What is the P of n? If you have the understanding of that thing, then write that understanding. But sometimes the things which will be given to you, it will be so much complicated that you cannot say something in simple words. So that's why, but this is the first example, so that's why we are saying something different here. Let P of n, we are just supposing, let P of n be the proposition. And what is that proposition? That the sum of the first n positive integers, this is sum 1 plus 2 plus 3 plus 4 plus 5 plus up to n. This is the sum of first n positive integers, which is 1 plus 2 plus 3 plus and so on there, is the right hand side, n into n plus 1 divided by 2. So this is the proposition now. If you don't want to say that sum of the first n positive integer, leave it. You can just say that let P of n be the proposition that 1 plus 2 plus and so on plus n is equal to n into n plus 1 divided by. You can write like that. If you don't want to say sum, you can say that let P of n be the proposition, write the left hand side, then use the word is equal to and right hand side. If you have this thing, if you have the equality is there. If there is inequality, then you can say less than or greater than or whatever. If there is some other symbol, you can say that same symbol. Anyhow, so now this is Pn. So this is easy step. And now the basis step. Basis step is also again an easy thing. It's not a different thing. So if you will see on this, so the first number is what? All these are integers. And the first number is 1. This is your first step. This is your basis step. Okay. The first number that you have here is your basis step. So that's why we are saying that P of 1 is true. Why? How? Because put 1 on the left hand side and 1 on the right hand side, and then if both sides are equal, then it is true. We have only one number, because in the basis step we are checking that proposition only for number 1, only for one number. So it means that on the left hand side you have only 1, you are taking one number, and then put this 1 on the right hand side. This would become 1 into 1 plus 1 divided by 2. So you can say 1 into 1 plus, this is the left hand side. Okay, and this is the right hand side after putting 1 into this equation. On the left hand side we have only one number, P of 1. We don't have n numbers because n is 1. So if n is 1, so this is our first number. Okay, again, so this is our one number. So we are saying that it is true because here the left hand side is only 1 and it is equal to 1 into 1 plus. So this is 1 plus 1 is 2. 2 divided by 2 you have on, again after valuation you have 1 here. So left hand side is equal to now right hand side. So left hand side and right hand side is equal when you put 1 into this equation. Understood or not? Any confusion in the basis step? Any confusion? Because this is the first example, so I'm asking. In next example, I will not ask. I will go with the speed, okay? This is any confusion up to now in basis step. Clear? Then inductive step, step number 2. I have just highlighted with 1, 2, and 3. Otherwise, it is not needed. It is, I just highlighted for your understanding that these are the 3 things that you have to keep it in your mind, that you have to do it. These are the 3 different steps. Anyhow, inductive step. Due to this inductive step, we have this name mathematical induction. Okay. First you have to, I told you that you have to assume something in the inductive step. You have to take some assumption. And what is that assumption? P of k. P of k. Sorry, this k is going to the next slide, but it is P of k. You have to assume something like P of k. And then on that assumption, you have to show P of k plus 1. And if that would be true, then you can say that something P of n is true for all positive integers. So now, these words are, by the way, not needed, but this is the first example, so that's why. So for the inductive step, now we are going to assume, that P of k is true for an arbitrary integer n, or for any integer n. Arbitrary mean random. Okay. So this is what you have to, if you are writing this problem, just for example, as a good answer, you have to write it first. We assume that P of k, for example, in the basis step, you said P of k is true. You are not assuming, you are saying true, because after evaluation, you can first evaluate and then you can say P of 1 is true. That is also okay. But in the inductive step, first you have to assume. You have to, so what is that assumption? P of k. Then you can write, we assume that P of k is true for an arbitrary integer or number, arbitrary positive integer. What is the domain? The domain is positive integers. So you can say that we assume that P of k holds mean true, is true for any arbitrary positive integer k according to the domain. This is what according to the domain. This k we are using, so you have to use the k here. And if you will assume that k is true for any positive integer, then you have to put k in place of this n, and then what? What will be the form of this equation? That will be the form. Because now k is not defined. K is not 1, not 5, not 4, not 7. So I cannot say anything. It is arbitrary. So that's why you have 1, you can start from here, 1 plus 2 plus and so on, and then you can put k in place of this k equal to, and then k plus 1 divided by 2. Just put k there, because this is assumption. We are not doing anything. After putting that k into that given problem, you have this form. This is just assumption. This is what? This is our assumption. Now, based on that assumption, you have to, under this assumption or based on that assumption, we have to show that P of k plus 1 is also true. This is what you have to do. Because this is what? We are on the ladder, we are at step pk, and then we have to say that we can reach at pk plus 1. So we have to show that pk1 plus 1 is also true. So this is the statement that true. But for this truth, you have to evaluate its truthness, like that P of like you did with the P of 1. So now, based on this assumption, under this assumption, you must have to show that P of k is also true. And how you can say that? Look at here. How you can, k plus 1 is the next step after the k, So that's why 1 plus 2 plus and so on plus k, and then plus k plus 1 is the next step. Just write it. We are writing now with the k plus 1. We are just adding that k plus 1 in that k, you can say. We are just adding this k plus 1 here. Just putting that. We are not doing anything, just putting. But this is not the proof, okay? So previously we have that k, and then k plus 1 is equal to, here with this n, put this k plus 1, and then you have the bracket, and then with this n, put this k plus 1, and then plus 1, and the divided by 2 according to that right hand side. Nothing else. You have now put the k plus 1 in that equation, nothing else. And then what? You can write that into this form. Further, this is, open it up, and then 1 and 1 will become 2, and then you can write k plus 1 and k plus 2 divided by 2. Now we are at this time. We have not proved anything yet. We are just putting the values. So after putting this k plus 1 here in this equation, we have this form. So this is what we have to prove. By using P of k, because that is our assumption. So now, here, okay, take this side. Take this side, which is the left hand side. So 1 plus 2 plus and so on plus k, that is. And now, you know that this 1 plus 2 plus k is equal to what? This one. K into k plus. This is your assumption. And now you are going to evaluate. You are going to prove it. So you have to use your assumption. What you have supposed, what you have assumed, you have to use your assumption. So up to this point, we are putting this assumption here. So this is equal to k into k plus 1 divided by 2. And this is what remaining, k plus 1, which we want to add. Now, after the simplification, take the LCM, whatever the LCM you can take it. 2, this would be the same, k into k plus 1, because 2 with this 2 and 2, this would be cross, you can say, after taking the LCM. And that would be the same thing. And then here, with that one, you have to multiply this 2 into k plus 1. 2 into k plus 1. And simplify it further. So this is k plus 2, and the k plus 1 is common. So k plus 1 is common and k plus 2. And that divided by 2. This is what you got. This is what you have to prove it here in k plus 1. This is what you have to prove it. So you have taken the left hand side, and after modifying that left hand side, you have reached the right hand side, and that k plus 1 is included. So this is what you are doing in chapter 2 and chapter 1. You have to take the left hand side after modifying and using some rules. You have to convert it into the right hand side, and if you have that right hand side, then you can prove something, that this equation holds, that this thing holds, that this thing is true. So now, when you started with the left hand side, when you reached at the right hand side, this is what you have proved, that k plus 1 is true. If pk is true, which you have assumed, now you have, when you reach at the right hand side, you have proved that k plus 1 is also true. This last thing. So based on the assumption, for example, this was our assumption. Based on that assumption that pk is true, if pk is true, then pk plus 1 is true. So now after this thing, now you can say that pk plus 1 is also true based on our assumption pk. And now what is the last statement you can say? When you have shown that basis step is also true and inductive step is also true, what is the last statement you can say? This first thing that you have supposed, P of n, which is your propositional function. Now you can say that our propositional function P of n, which is equal to this equation, is true for all positive integer n. Now you can say, or you can say, we have proven that this equation is true for all positive integers n. So this is the first example of mathematical induction. And in the mathematical induction, you have the two steps, the basis step and the inductive step. And before starting this basis step and inductive step, you have to suppose your propositional function, which would be given in your question or problem. Now, example 2. So I will ask these questions like that. Use mathematical induction so that you can have that idea that how you have to solve that question. So use mathematical induction to show that 1 plus 2 plus 2 raised power 2 plus and so on plus 2 raised power n. So each time maybe the power of 2 is increasing, okay? Each time here the power of 2 is 0. 2 raised power 0 is 1. 2 raised power 1 is 2. 2 raised power 2 plus and so on 2 raised power n is equal to, so that is equal to 2 raised power n plus 1 minus 1. Minus 1. So what this equation is saying that, okay, if you have the powers of 2 and if they are summing it up, you can calculate their powers and then sum it up. But this is the right hand side. From this equation, from this formula, you can calculate the result just within one step. 2 raised power n plus 1 minus 1. Just take the last number, add it 1 into it, calculate the power and and then subtract 1 from it, and then you will have your answer. So here, so this is something, a conjecture or something which is a small theory given to you, an equation given to you, which is, and it is being said that this equation is true for all positive integers n, non-negative, positive. Non-negative means positive. Positive integers n. Now you have to prove it using the mathematical induction. The same thing again. Again, the basis step and the inductive step. So now proposition is what? Let P of n be the proposition that this left-hand side, you can write it, is equal to right-hand side for the non-negative integers n. So this is the easy way to say the proposition without understanding, okay? Without understanding. What is this thing going on here? If you don't have that understanding, this is the second way to say that. Let P of n be the proposition that this left-hand side is equal to, write that equation, is equal to 2 raised power n plus 1 minus 1 for all the non-negative integers. So this is our first proposition. And now the basis step. You have to identify the basis step with care, okay? Because here a mistake can happen. So you have to look over here, and then you will have the understanding that it is the power of 2. This is 2 raised power 2, 2 raised power 3, and so on, 2 raised power n. This is 2 raised power 1. This is 2 raised power 0. That is becoming 1. So here the basis step is now P of 0. Your n is now 0. Because this is the first number, and how you are getting it. So P of 0 is, we are saying that P of 0 is true. And then you can give your proof how it is true. Because 2 raised power 0, which is 1, is equal to put 0 here. 0 plus 1, 1, 2 raised power 1, which is 2. 2 minus 1 is 1. 2 minus 1 is 1. So left hand side, right hand side is equal. So P of 0 is true. This completes the basis step. Okay, alas. Next, inductive step. And what is the inductive step? First, you have to assume Pk, and then you have to prove Pk plus 1 based on that Pk. So we assume that inductive step, inductive hypothesis, this is called inductive hypothesis, Pk. Pk is called inductive hypothesis. And this Pk plus 1 is actually the inductive step. So we assume that inductive hypothesis, Pk, this is our assumption. You have to do it like that. So Pk is true for any arbitrary integer n, same. So Pk is true for any arbitrary positive integer or non-negative integer, just playing with words, nothing else. Integer k, and if it is, then you have to put that k into that equation, and you have to make some form of that equation. So 1 plus 2 plus and so on, 2 raised power k is equal to 2k plus 1 minus 1 here. So that is now the form of our assumption of our Pk. Now, based on that assumption, what is our assumption? That Pk is true. If Pk is true, then Pk plus 1 is also true. This is what we want to say. This is what we want to prove. So we are saying that Pk plus 1 is also true. But this Pk plus 1 is true, we have to show that. You have to show that it is true. You have to evaluate. And by putting this Pk plus 1 after this k plus 1, by adding, you can say by adding this, because that is the next step. You can add or you can put it here. It is up to you. If you will put, for example, 2k plus 1, then we know that k plus 1 is already there because this was the previous step. So it is always better approach to use the addition here, because we don't know either you are going to use that step or whatever, because you have to evaluate, and that evaluation can go in any direction. It is not always that you have to modify the left hand side and reach at the right hand side. Maybe sometimes you have the other approach. So here, so 2k was the previous thing, and then you are adding. If you will put k plus 1 into the end, that would become plus 2k plus 1. 2k plus 1, that would be the next step, is equal to, put here k plus 1. K plus 1 plus 1, k plus 2. 2k plus 1 plus 1 minus 1. We're putting k plus 1 here on that one. Just put k plus 1 here. And that would become what? 2k plus 2 minus 1 after putting k plus 1 here. When you are putting k plus 1 in this equation, keep this previous step, show this previous step always. Sometime it can happen that you will not show, you just put k plus 1 here, and then you will have 2 plus 1 plus 2 plus 2 raised power 2 and so on plus 2k plus 1 directly. So always show that previous step, because you don't know when that step is needed to you. And if that step is needed to you, And if you have not mentioned here, then you can do some mistake. And then you cannot modify your left-hand side thing to the right-hand side thing. So this is what I am saying. But what I am doing here, I am just putting that k plus 1 here in that equation. Or I am adding. Or I am adding. These are the two approaches. Either putting or adding, whatever you have. So now this is what we have to prove, okay? This was our assumption with the pk. This was our assumption with the k only. And this is now our form with the k plus 1. Whatever the left hand side and whatever the right hand side, this is our right hand side finally. So now we have to prove that this is actually there. This is what you have to evaluate. So that's why I am taking this left hand side. 1 plus 2 and that one, this is the left hand side. This is the left hand side. So now again, up to this thing, 2 raised power k. So I am just separating that up to k and then the last term which you have added, 2k plus 1. This IH mean inductive hypothesis. Okay. This is not necessary to mention. I have just mentioned here only in 1 or 2 examples, rest I am leaving it. Now, what is this one? 2k, 2k. What is this one? This is what you have here for k. This whole equation up to 2k is equal to 2k plus 1. So this is what I am putting it here. So this 1 plus 2 and so on, 2k is equal to 2k plus 1 minus 1. And this is what the remaining. And then now simplify it. And then what? This is one thing. Just if you remove these brackets, and this is second thing. So 2 raised power k plus 1 appearing in that thing 2 times. So according to that mathematical sense, so this is 2 multiplied by 2k plus 1 minus 1 after simplification. And this is basically what? 2 raised power 1. This is what? 2 raised power 1. Which now, what you can do now? After further simplifying, you have 2 raised power k plus 2 and then minus 1. This is what you have to prove it here. This is for the pk plus 1. Okay. This is for the pk plus 1. I have already told you. We have started with the left hand side. After simplifying and modifying, we have reached at the right hand side of this pk plus 1. So when you read at the right hand side, when you will reach at the right hand side and it is equal, then you can say now it is true. So now at the basis step and inductive step are now complete. And then what is the last statement that you can see? Now you can say that P of n is true for P of n, whatever our P of n is this one. So now we can say that our P of n is true for all non-negative integers n. So this is the last statement that you have to say. Now, moving on, example 6. So first you have seen example 1. Example 2, I am just leaving it for you. Example 3 again. 4, leaving it for you. 5, leaving it for you. And now I am on example 6. And then I will say, read and understand these examples. I have not marked your paper yet, but the feedback after the exam which I have, maybe the exercises which I have given to you, maybe it's an issue for you. I don't know. Because 4 or 5 students just say this thing to me, which I am sharing with you. So now what I am doing, I am only giving you the examples, which is available in the book. Which is available. The solution of the examples is available in the book. You have to focus on that. You have to. So now you will read the book actually, which you are restricting yourself. Now you will read your book. So now example 6. Again, use mathematical induction to prove that 2 raised power n less than n factorial. This symbol means factorial. 2 raised power n less than n factorial. Now we don't have any series. We don't have that left-hand side. We have the left-hand side here, but here we don't have the equal operator. We have the unequal operator, less than operator. We have the left-hand side and we have the right-hand side, but we don't have the series. So use mathematical induction. Just take a break and then I will start, because take a break. So example 6, use mathematical induction to prove that 2 raised power n less than n factorial. For every integer n, so you have the domain always positive integers. For every integer n with n greater than or equal to 4. So now your value, the starting value for your n is 4. And then it can be greater. So this is what written here. So now solution. So first you have to suppose your proposition. So P of n be the proposition that this one, 2 raised power n less than n factorial. For every integer n with n greater than or equal to 4. Just write that statement and represent it with P of n. So according to this condition, our starting number is 4, n greater than or equal to 4, due to equality 4. So that's why P of 4 is, now we are saying P of 4 is true, because put that 4 here, 2 raised power 4, we have 16, less than 4 factorial. What is the factorial of 4? 4 divided by, multiplied by 3, then multiply with 2, then multiply with 1. And then what do you have? 24. So 16 is less than 24. That is true. Now you have the condition less than. So 16 is less than 24, which is the factorial of 4. So it's true. Now the inductive step. So inductive step, you have to assume first for pk, and then you have to prove it for the pk plus 1. So inductive hypothesis is what pk is true for any arbitrary integer k with k greater than or equal to 4. Sorry, this is greater than or equal to, okay? That is, now what put k in place of this n, and you will have your equation 2 raised power k less than k factorial. So this is our assumption. Now we have to prove, if pk is true, we have to prove this equation for pk plus 1. And then this equation, after putting k plus 1 in it, how it will become? It will become 2 raised power k plus 1 less than and k plus 1 factorial. So this would be the situation of that equation after putting k plus 1 in it. So this is what we have to prove. This is what we have to prove. So now I will take the left hand side as we did in the previous examples. So after taking that left hand side, I can rewrite this left hand side with 2 raised power k and 2 raised power 1, like that. This is equal to that thing by definition of this exponent. This exponent is k plus 1. So by definition of exponent, we can rewrite this thing like that. And then this 2, now this 2k plus 1, we have reached at this previous 2k plus 1. So we are again, actually we want to represent it with 2k. And that 2k is what? Less than k factorial. So now we are going to replace that 2k, 2 raised power k. So 2k is with k factorial, which is that one. And if we will replace, then we cannot use this equal operator. What is the operator here? Less than. So that's why the operator is also changed. Then it's okay. Because, for example, this 2k is less than k factorial. So we can replace it, but then operator will be changed. Operator will be changed because it is our assumption that 2k is less than k factorial. So if you want to use that equation, then this equal operator will also change. And then, so this is what you have done by using the inductive hypothesis. This is our inductive hypothesis. And then we are going to say something about this too. What is the condition here? N greater than or equal to 4. If n is k plus 1, what is this k plus 1? K plus 1 is greater than or equal to 4. What is the value for the k plus 1? 4 or greater. And 2 would be less than this k plus 1.